All right, so hello, welcome to class. It's Wednesday, April 8th. At least I think it is. I keep messing up my days. So we do have Friday off. So Friday is a holiday, so we won't have class Friday. So that means we're going to have class on Monday. So I won't be here Friday. Everyone has a day off. Just go relax. Just, I don't know. You can't really go out and do anything, but yeah, maybe sleep in. So that's coming up. The other thing, um, as I post these, it's been kind of a lot of time to give you time in class to work through the problems. So I'm going to start posting the problems beforehand, and I want you to work through the problems before class. That way we can just kind of get to class and go through them, and you don't have to be stuck in class with me for as long. You're always free to stick around if you have questions afterwards or things like that. So don't feel like I'm trying to kick you off or anything. So if you still want to hang around and ask questions after I finish recording, you can still do that pretty much anytime. But yeah, so I'm going to post the questions beforehand. I'm going to keep doing the two questions beforehand a day or two before. You'll go through, work them, and then you'll show up with them worked, and then we'll go through them. Um, I posted a really good example response for this, so let's kind of go through that real fast. So we have an example response here. I deleted the name, but yeah, we'll go through. You write your first and last name in pen. It'd be really good to have a title with the problem. Go through, clearly organize your work. Again, you don't have to write the question, but see how it's clearly organized. You should attempt your work before looking at the key. You need to attempt your work before looking at the key or before looking at the video that I'm posting right now. So if you haven't done your work yet, you should be doing your work now. And then once you finish the problem, you can go through, grade it, look at the key, watch the video, or log in to the live class. You'll go through, you give yourself points. One thing, you cannot earn half points. So you can't earn half a point. If you say this one was worth 1 point and you got one graph right and the other one wrong, that's 0 out of 1 point. So you cannot earn half points. You go through, you grade it. So this person got 5 out of 7 points. So because they got 5 out of 7 points, A and B, they got all points. So they clearly labeled on a separate sheet of paper, all points earned. Or it doesn't even have to be a separate sheet of paper, but just not in the exact same area. So they clearly labeled all points earned. But C, they missed some points. So they got 2 out of 4 points. So because they missed some points, they went through and redid that part of the question in a way that would earn them all points. Okay, so they did that. Then they did their next problem. They attempted this without looking at the key, but they did really well. So they ended up getting all 7 points. They went through, they showed all the points they got. I don't need you to write why you got the points, just write a number next to the point should be sufficient. So they got all 7 points. They clearly labeled they got all 7 points. And then because they clearly labeled it, I don't go looking off somewhere, oh, hey, where's your correction? They clearly labeled they earned all 7 points. And so I'm not going to look for all the other points. One thing I've noticed is quite a few people got perfect grades that I wouldn't necessarily expect to get perfect grades, like not trying to like doubt people's ability or anything. Uh, but yeah, the grades you get on this shouldn't be way higher than all of your test and quiz grades. I expect to see points lost here and there. So if it's someone who doesn't always have the highest test or quiz grades and is always getting a perfect score on these, I'm not going to be giving you very many points because you really should be attempting this without looking at a lot of other things. All right. So you should be attempting these without looking at the key. Give it your solid attempt. Again, as long as you put a solid attempt, I don't care if you miss everything. As long as you do your solid attempt first, then you go through, you grade yourself, and then you do a corrected response. All right. So this is posted here. It's the top thing in your stream. I go through some things that I've noticed that people didn't do, and I gave a good example response. All right. So hopefully that's clear. Let's go through these then. So again, I do want you to do these beforehand before you get to class. That way we can go through class a little bit more and you don't have to spend as much time logged in here if you don't want. All right, so let's look at this. I gave you two 25-minute questions. So these are the first question you're going to see on the AP test this year. You're going to have a 25-minute question, work through it, have 5 minutes to upload, then a 15-minute question. Now, this is an experimental design question. You're not going to have an experimental design question on this test, but there's still a lot of parts of a question like this they can put. So I'm not going to focus so much on the procedure, but there's still some important things to go through on this question. All right, so let's look at it. We have a new kind of toy ball is advertised to bounce perfectly elastically off hard surfaces. A student suspects, however, that no collision can be perfectly elastic. The student hypothesizes that the collisions are very close to being perfectly elastic for low speed collisions, but that they deviate more and more from being perfectly elastic as the collision speed increases. So A wants us to design an experiment to test the student's hypothesis about collisions of the ball with a hard surface. The student has equipment that would usually be found in a school physics laboratory. Now, starting off here, and you should have given yourself 25 minutes to do this. What's the key word here? There's a key phrase, but there's a specific word that we're really looking at. Collision. So it is a collision, but that's not the biggest thing. The biggest thing is perfectly elastic. So when we see the word collision, we're normally thinking about momentum, right? Normally when we're thinking of collisions, we're thinking about momentum. But here we're talking about perfectly elastic. What is perfectly elastic talking about? Yeah, total mechanical energy conserved. So TME conserved. But normally when we're looking at a collision, we're mostly looking at kinetic energy being conserved. So if they just said the word collision, our mind should be kind of going to momentum. But because this whole thing is revolving around the fact that is this perfectly elastic or the student doesn't think it's perfectly elastic, we're really talking about this perfectly elastic part is what we're trying to test. So we're really seeing is our mechanical energy conserved and particularly kinetic energy. So when the ball goes down, does it have the same amount of kinetic energy before hitting the ground and after bouncing up off the ground? So we're trying to see that kinetic energy right and before and after the collision. So to design an experiment to do this, we're really trying to figure out something that would measure kinetic energy before and after. So kinetic energy is 1/2 mass times speed squared. So what are things that we need to measure? All right, so we need to get mass and velocity. So mass, and we don't really need velocity. I'm going to say speed just because speed squared, we don't need direction. So we need mass and speed. If you write velocity, that should just be fine. 2 wants to know what equipment we would use to get mass and speed. That's one way of doing it. Or you could do initial height. So one way of doing this is kinetic energy 1/2 mass times speed squared. Yeah, now that I think about it, why are you talking about initial height? Or change in height before and after the bounce. So when this drops, I have gravitational potential energy turns into kinetic energy, bounces back up. That kinetic energy turns back into gravitational potential energy. So we could also look at, let's put the or right here. Or if we're looking at gravitational potential energy, mass, acceleration of gravity, height, or we could get mass and initial slash final height. Okay, so when we're talking about these two, so 2, what equipment would we use? I'm not going to spend a whole lot of time on this because we're not going to have an experimental design question on the AP test. So obviously for mass, we would use a scale or a triple beam balance. You could just say an electronic scale. It doesn't matter. Just something to measure mass. What would we use to get speed, though? Speed is going to be a tricky thing to measure. Height initial equals height final. Yeah. Yeah, you could actually just do that. Yeah, you actually shouldn't. Do they expect you to get mass? That's a good question. Because, yeah, you should be able to prove just this equal and opposite heights. Yeah, you're right. Because we're proving energy conserved, yeah, mass isn't changing. mgh initial equals mgh final. So yeah, we don't need to measure that. Or 1/2 mass times speed initial squared equals 1/2 mass times speed final squared. Yeah, so because mass isn't changing, yeah, so all right, so we don't need mass. They won't take points off if you write the mass there, though, because that would be proving that they have the same. Uh, you, it depends. You could measure speed right before and after after it hits the ground, or we could get initial and final height. So if we could do either. Either of these should work. So if we do speed, how would we get speed? Speed is going to be harder to get. This is the hard route. And then this is the easy route. Well, yeah, but we would have to. Yeah, so that's why height is going to be easier to get. So yeah, we could do a slow motion camera with the timer. That's one way. Timer and meter stick. Which means we're going to have to add a few more things in here for speed and height and time. And so yeah, we could go through here and we could say for a small distance right above the ground, yeah, so this would also kind of go into 3. So we would say use a small change in height above the ground. So the speed is going to be that change in height over time, and then use timer to get the time. And so yeah, it's important that you would use the small amounts right above or below the ground. So I'm not going to go super in depth again, not going to be on the test, but yeah, it would be something like that. So I'm not going to focus on this part. But yeah, it's going to be easier. So this is a hard route. This is the easy route. It would be much easier just to get your heights. So height with a meter stick. And then 3, we could just compare drop height to the final bounce height. With the meter stick. But yeah, that's all you really need to do. So this is going to be a lot easier to do using your potential energy initial, because if it's perfectly elastic, all this potential energy I start with turns to kinetic energy, all the kinetic energy is returned, so it should all go back to potential energy. So yeah, that's going to be a little bit easier to use. Again, this is not a good procedure, but because procedures won't be on the AP test, I'm not going to spend a lot of time on this. So you can go through and actually look at the rubric. I'm sure I did not hit all the points here because I wasn't careful. So 1, 2, and 3 were all scored together on this one. So if your plan uses the quantities to compare, so if you get enough quantities that can be used to do it. So you're either going to need to talk about the speed right before and right after the collision, or the height that is dropped from and the height that it bounces to. Conceptually plausible plan to measure pre and post collision positions and or speeds that could be used to compare pre and post collision. So this would be something about measuring the drop height with a meter stick and the bounce height with a meter stick, or using small distances. I can't use the entire height this is dropped for speed, right? If I'm doing speed, I need to get the distance traveled right before hitting the ground, distance traveled right after hitting the ground. So if it falls, say it falls like an entire distance, I really only care about this small distance before and after hitting the ground. I don't care about the entire height dropped, just the small distance before and after. So that's important if you use speed. You didn't have any extra equipment or measurements. I would say maybe they include mass here. I would say mass wouldn't be included. That's just me because you would actually be proving the energies are the same and actually calculating. Because if you were proving same energies, you probably would still measure the mass and calculate energies and all that. I would hope they don't take points off of that. So lab equipment and measurements well specified. So that's talking about what you use to measure what. So if you said use the meter stick, you would have to say I use the meter stick to measure the initial height and the final height. Um, and then trials. So yeah, you always need trials. So this one, because yeah, that's an important thing I missed. So they're saying for different speeds, right? So if you're writing a procedure, you would have to say for different heights, right? If I drop from a high height, I have a high speed. If I drop from a low height, I have a low speed. So that's important. You would have to say you drop from a lot of different heights. So if you drop from a low height to get low speed collisions, drop from a high height to get high speed collisions, and then you go through a lot of those. All right, so going through this real fast, again, don't care so much about that, not going to be on the test, but I think other parts of this question could show up on the test. So something like B, I could see more showing up. So B, describe how you would represent the data in a graph or a table. Explain how the representation would be used to determine whether the data are consistent with the student's hypothesis. So I'm going to go with the easier one, which is our heights. If you used our speeds, it should be a pretty similar type thing. So B, so a data table, just something like the height dropped, so height dropped, and then height bounced. Wait, no extraneous equipment. Okay, so no extraneous equipment or measurements. I personally would think that a scale would not be extraneous, even though I crossed it out here. I could use my scale to get mass, and then I could compare energies, and so I don't think that would be extra. But if you said something random, like what's something really random? You need to measure the horizontal distance you are from the wall. That would be silly. You need to measure the yeah. I mean, just something really like what's something really random? I can't imagine. Um, yeah, measure your height. Those are kind of silly ones. Like I'm trying to think of like a specific thing someone would say to measure that wouldn't be relevant. Um, yeah, so I guess if you're speed, but yeah, you could use speed. I guess if you were trying to say measure, let's say you're trying to instead of the speed, because our speed, we want our speed right before from here to here. So like we're talking about really small distances to get our speed. If we're saying measure our entire height and use that to calculate speed, I would say that's extraneous. Or just yeah, like just any random thing you say that doesn't contribute to the procedure. If you say measure something and it doesn't help you directly calculate or measure something that can prove this, then that's extra. Um, Yeah. All right, so we have drop height, drop bounce. Or we could do like a graph, height drop, height bounce. And then this is really describe how you would represent the data in the graph or the table. So we could say I would create a data table comparing those two, create table or graph for drop height versus bounce height. And then here's where we kind of get into what would be different about these. How would I use the representation? So for the table, we would look if height drop and height bounce are the same. For the graph, this would be a little bit different. We would have height drop on the y-axis and height bounce on the x-axis. And we would see if the slope is 1. Right? Because if the slope is equal to 1, then that means that the drop height is always equal to the bounce height. Y is absolute value of the change in height. So wait, the thing went away. Yeah, that should work. So x is your initial height, y, and then so your x is the initial height, and then the y is the change in height. So I would be a little bit more specific about what you mean by change in height. So you're talking about I wouldn't call that change in height. I would call that drop height minus bounce height or something. And then if it's constant 0, and then yeah, so you would try to see a constant 0, then it's manufacturer correct. So yeah, tan, that would work. Just I wouldn't use the words change in height. I would say drop height minus bounce height. Ball's potential energy before dropping and bounce back after is good as well. So this is where it's kind of tricky. If you say potential energy, then you had to have measured mass. If you didn't measure mass, then you can't compare potential energy. You would have to compare heights. So I would say if you didn't measure mass, you can't use potential energy in that graph. A3. If you define your change in height, if you define it in one part, I would redefine it or explicitly state it somewhere. I would still write it if you did that and you use like delta H. I would just write it here again. That's the height drop minus height bounce, just to make sure. Usually they grade these one at a time. So if you use something again from a previous part, you need to reference it in the next part. Let's go through this. Yeah, so this is one of the most vague questions. I heard people who actually graded this question absolutely hated it because this part was the most vague part to grade whatsoever. For describing how to plot or otherwise represent the data in a way that could be used to test the hypothesis. So that's why there's a lot of different ways. You could use a chart, you could use a table. I was comparing drop height to bounce height. That should work. Tan was comparing the initial height to the difference between the initial height and the bounce height. That would work. There's a lot of different ways to test this. So for describing how to compare post-collision and pre-collision mechanical energy or a plausible alternative to quantify the elasticity of the collision. Um, so this is where I didn't quite go into that, but yeah, you would have to talk about something about how to actually calculate your energy. So yeah, I guess I really should talk about. It's just weird to me. I don't. Yeah, I would do something like talking about, well, mgh initial equals mgh final if it's elastic. And then that means I don't have to compare mg because mass is constant. So you could talk about comparing these two values. The mass is constant, so all I need to compare are the initial and final height to prove they're the same. I would write that explicitly. Either that or you had to measure the mass and then say these two should be the same. And then for comparing low speed versus high speed results, so yeah, if you put that in your procedure, you should have that there. But yeah, you would say something about look at the results for the low speed would be the low drop heights, high speed would be the high drop heights, and then you either need to look at something like this. So a slope that was on my graph for drop height versus bounce height, the slope should be one a ratio. So that would be something like um, doing drop height divided by bounce height, which is pretty much what a slope is just a ratio, or difference in the values. So that would be like what I was talking about with my chart. Are the values staying the same, or is the difference between the values getting bigger and bigger? Um, so yeah, here's some examples. Again, not going through this so much because, again, not going to be on the AP test, but just a good thing to kind of be thinking about because I could see aspects of this showing up on the AP test. Questions on B. No questions. Just grade yourself and try to get a good enough answer on this one. C is kind of what I like more. The kind of thing I might expect to see on the AP test, and the reason I still gave you this question mostly. So C, a student carries out the experiment and analysis described in parts A and B. The student immediately concludes that something went wrong in the experiment because the graph or table shows behavior that is elastic for low speed collisions, but appears to violate a basic physics principle for high speed collisions. So first of all, what's the principle that's violated? Conservation of energy. So violates conservation of energy. I could see them asking you a question like this on this year's AP test. It could be momentum, but the problem with momentum is everything about this question is revolving around that elastic collision, and because everything revolves around is this elastic or not, we're talking about energy here still. I agree with you. It could be momentum is not conserved, but I'm pretty sure for this one they gave 0 points for talking about momentum, which in my opinion is kind of silly. But just kind of realize they're still talking about energy because that's what we've been talking about the whole time. But yeah, it, if conservation of energy isn't, if energy is not conserved, momentum probably isn't either. So if this is violated, what would I say about my energies then? Final height greater than initial height. Yeah, anything about my final total mechanical energy is going to be bigger than my initial total mechanical energy. So I have a much bigger final total mechanical energy than initial. So a table or a graph that would indicate the nearly elastic behavior for low speed collisions, but violate for high speed collisions. So yeah, so like you said, final height greater than initial height. So for final height and initial height, let's just say in centimeters, or drop height versus bounce height. Low speed is going to be small drop. I drop this 10 centimeters, it bounces 10 centimeters. That would be perfectly elastic, energy conserved. Let's say I drop 20 centimeters and it bounces 20 centimeters, perfectly conserved. 30. But let's say we start getting more energy back. That would say it Why did I put final initial? I meant to put initial and final. Initial over here, final over here. And then it bounces up 31 centimeters. That would be weird. Or it drops 40 and it bounces up 42 centimeters. You drop it 50 and it bounces up 53, 60, 64, something like that. So as the speed gets higher, it's somehow bouncing up higher. So this is saying that energy is conserved for low speed collisions, but as my collisions get faster and faster, I end up having more final energy than initial. Or if you did a graph, which honestly I think most people would do a table, but drop height versus bounce height. So we would see low speed collisions, something linear with a slope of 1. But we see here as my drop height gets bigger, my bounce height is going to get bigger and bigger. So I'm going to see something like this. Maybe not so extreme. But we're going to see our bounce height goes up a lot while my drop height goes up a little. Or for Tan's graph, you would just see a value above 0 if you're doing your difference in heights. And then actually, now that I think about it, your graph would need to change a little bit for this one. You would not want to use absolute value tan, because if you use absolute value, then that couldn't differentiate which of the energies was bigger. So you would need to change your graph a little bit. Yeah. And there's nothing stopping you from going back in a question and changing some things up. I plotted change in potential energy and speed. That's a weird graph. Did you measure anything about speed in your procedure? Is about the only thing. If you didn't measure anything about speed, then you can't really use that. Change in. Yeah, that's a really weird graph. For this one, because we're comparing energy before and after a collision, we really want the same thing on our x and y axis or something really similar. So I would graph energy versus energy, or speed versus speed, or height versus height, something like that. For this one, I wouldn't be mixing when I'm putting on my graphs. All right, so yeah, so your table or graph has to show collisions that are perfectly elastic for low speeds. So a graph with a linear slope of about 1, or a table that shows final height and initial height are the same, or the initial speed and final speed are the same. But then for the higher speed collisions, something has to happen showing that you have more energy afterwards than you had before. And then, yeah, 2, the physics principle that appears to be violated and why that's violated. And then, again, everything about this has been talking about elastic collision. So this is going to be conservation of energy. And then this would be something, several physics principles might appear to be violated, but you only need to identify one. Maybe they do take momentum for this one also. So state 1 physics principle, I'm mostly conservation of energy is what they're trying to get at, and explain what aspect of the graph or table indicates the physics principle is violated. Pretty much both of these I'm using the same thing here. It's talking about how my final height, that height bounced, is greater than the height dropped, implying, I think that's how you spell implying, that total mechanical energy final is greater than total mechanical energy initial. Boom, kinematics. Not so much kinematics. So you can't ever actually violate kinematics because kinematics is just a mathematical relationship. So it's just math. So you can't ever violate kinematics. You can use kinematics incorrectly, but it's actually impossible to violate kinematics. Um, so correct description of the aspect of the graph or table that shows a violation of the physical principle indicated. So something showing that your bounce height is bigger than your drop height, or rule is what's rule 33 that you're always correct, or I don't know, I don't remember all the rules. For a correct explanation of why the representation shows a violation of the principle involved. And so that would be just something talking about my table here shows that my final height is higher than my initial height, or this is saying that I have a bigger bounce height compared to my drop height, something like that. Questions on this first one? So I didn't go super in depth on that for a reason, because you're not going to have a procedure on the AP test. This next one, though, is a type of question you can expect to see on the AP test. This is a QQT type question, a qualitative quantitative translation. So we'll kind of see how this goes through. So qualitative is just what will something look like. Quantitative is do math with an expression or numbers, and translation, if I change this, how will that change? All right, this is a horrible question that absolutely messed everyone up on the AP test. So yeah, I don't know who designed this question, but they were pretty much like, "Oh, ramp? Everyone in physics does ramps, right? Let's ask this in a way that no one is going to understand what the heck is going on." So, we have a ramp that someone decided to put bumps on. A long tramp inclined at an angle theta to the horizontal has small speed bumps on it. Is it okay if I don't use the camera? I would say for camera, you definitely need to use a camera for the speed one. Otherwise, you're not going to get precise enough information. For the heights, you don't necessarily have to use a camera, but a camera would be useful for reducing error. So yeah, so small speed bumps. The bumps are evenly spaced at a distance d apart. Shown in the figure above. The track is actually much longer than shown, with over 100 bumps. I don't know why they felt the need to say that. A cart of mass m is released from the top of the track. A student notices that after reaching the 40th bump, the cart's average speed between successive bumps no longer increases, reaching a maximum value v average. This means that the time interval taken to move from one bump to the next bump becomes constant. Consider the cart's motion between bump 41 and 44. In the figure noted, sketch a graph of the cart's velocity v as a function of time from the moment it reaches bump 41 until the moment it reaches bump 44. Over the same time interval, draw a dashed horizontal line, v equals v average. Label this line v average. So, how many of you know what's going on with this question? And how many of you just looked at this thing like, what the heck are they thinking? Yeah, so the first time I looked at this question, I was thinking, what the heck are they thinking? Um, so, so yeah, they're testing speed versus time graph. Yeah, it's in a horribly weird way though. So let's try to put this together. So A is wanting us to draw a graph. Yeah, honestly, the first time I looked at this, I looked at it for like a minute or two before I like started working on it, which in my opinion, makes it a bad question because if I had to look at this for any amount of time before I figured out what the heck they were asking, then students were not going to do well in this one. I think the average out of 12 points, I think the average on this one was like under 2 points for everyone around the world. Yeah, it was bad. I think it was like 1.8 out of 12 or something. Um, okay, so let's look at a few things here. So we're looking at these bumps. So we have bump 41, 42, 43, 44. So what is the reason that they chose to start with bump 41? Let's start there. So not speed constant, but they started here because this is when our average speed becomes constant. So they chose that. At 40, the average speed becomes constant. So we have the same time intervals between these graphs. So that's a reason they did this. So the bumps are spaced apart. So starting here, so we start at a certain speed here. Now we're looking at speed versus time. No, it's fine. I mean, very like just a little semantics. Average speed is the same. So when this goes down the ramp, it's obviously going to speed up, right? So we expect this to speed up when it goes down the ramp. How does it speed up though? Is it going to speed up linear or a curve? Yeah, so we're going to see linear because between the bumps, our acceleration down this ramp is going to be g sine theta, right? Sine slides down the ramp. So we expect to see g sine theta between the bumps. Sine theta is a constant value, g is a constant value. So I expect a constant acceleration. So that means I'm going to have a constant change in velocity. So because I have a constant acceleration between the bumps, I have a constant change in velocity. So I expect to see something linear right here. But then I hit the bump. What happens to my speed when I hit the bump? It slows down. Is there a key phrase here? Yeah. So it slows down, but how much does it slow down to if the average speed is the same? So it does slow down here, but where does it slow down to? The same as the 41 beginning. So they kind of are putting this in a way that this is resetting, right? We have the same average speed. We notice after the 40th bump, the cart's average speed between successive bumps no longer increases. So we reach the point where it's hitting bumps so fast that it reaches a maximum speed. So it's going to keep resetting here. And then notice it doesn't happen instantly. It takes some time to reset, and then it's going to go up. It reaches the same maximum heat speed as it does before, and then boom, it resets back down to where it was, and then it reaches the same maximum speed, and then resets again. And if I was actually good at drawing, these would all be identical. Actually, I drew that a little bit low. But yeah, these should all look identical to each other. Struggle with bumps when you started driving. Actually, I really don't like how that looks. Let's extend this out like that. It goes the same height here, and then boom, resets. All right, so that's the first part. And then our average speed is constant, right? So our average speed is going to be a dashed line. Our average speed is going to be somewhere between our maximum and minimum speed. Average. And it should be a horizontal line. Did anyone get that? because I will be extremely impressed if you got that. Word constant got you. Well, the average velocity is a horizontal line, yeah. So if you did that, you were good. So let's look at the key. So having a constant upward slope each segment between bumps. So if you got this constant upward slope, you got a point. We're having the velocity reset abruptly at each bump to a minimum positive value that's the same. So it has to stay above the x-axis. So it resets down to the same value every time if we have the same constant velocity. You get a third point for having the same maximum value at each point occurs near the bump times. Yeah, so if you didn't draw like a sawtooth wave, like up, down, if you drew it like sinusoidal, you get the points. Near the bump, I guess I should have drawn mine a little bit before the bump. I guess, yeah, it takes time to go through over the bump. So I really should have shifted this over slightly. So really should happen where that's the bump. But yeah, something like that. And then for drawing a horizontal V average line and consistent with the graph drawn, even if the graph is wrong. So that average line has to be through the center. And even if you drew something really wrong for this one, as long as the average line is horizontal going between the maximum and minimum points, you got that. How many points did you get? Anyone like get those points? Yeah, right. I really don't like that question. I know another physics teacher that someone managed to get all the points for the graph. That's really impressive. I know a physics teacher was like not impressed with this question and they really disliked it. So they went and built a setup like this and it actually didn't even work like this. So this is an extremely contrived question that doesn't really even conform to reality. Yay. Did I get it when I first attempted it? I mean, I got most. I don't remember off the top of my head. I got most of them. I may have gotten them all, but it's just really weird. Um, yeah. Again, normally, yeah. Give this question to the AP test this year. Hopefully they don't do something like this. This is my biggest complaint with a lot of times in the AP test. They take a question like a ramp that everyone does in class, and then they change it up in a way that everyone just becomes confused. So pretty much every time I go through, I take the AP test right when they release it before they release the answers. There's 45 total points. I usually get like 44 or 45 of them. Sometimes I miss a point or two here or there, just from not being specific enough, or they're asking for something stupid that I thought was obvious, but I guess wasn't. B. So suppose the distance between the bumps is increased, but everything else stays the same. Is the maximum speed of the cart now greater than, less than, or the same as when the bumps were closer together? So we spread the bumps apart. What happens to that average speed? Or the maximum speed, I mean. Greater or smaller average speed? Yeah, why greater? Now, even if you messed up this graph, like imagine you have no idea what the heck is going on here, feel free to skip the graph and look around. Maybe the next part is a little bit easier. I think B is more easy to solve. So why do we get a greater, if I can spell, greater maximum speed? Yeah, you can use, exactly. This is a kinematics question. So why? There's more time to pick up speed. That's pretty much exactly all you need to say. More time to accelerate, I cannot spell today, accelerate, so more time to accelerate, and therefore faster maximum speed. It's pretty much all that was. That's just kinematics. It has more time to accelerate. I think they also took more distance to accelerate. Greater than, if you, no points for the correct answer, but if the explanation is completely incorrect or there's no explanation. Yeah, so nothing for the correct answer is all that's saying. No points are earned if you put the wrong answer. So yeah, here's sometimes if you really know the answer, select it. But sometimes here it's no points are earned if you put the wrong answer. Um, if you really know the answer, sometimes you need to put the answer to get all the points. But here, if you put the wrong answer, it doesn't matter what you write here, you get no points. So I would say if you really know the answer, put it, you're going to be better off. But if you're really unsure about the answer, it might be good not to select one of those and just talk about what you know. Just a thing you could do. If you're really confident, select the answer. If you're not confident, or if you have no idea, it might be better just to put things you know below that. So indicating there's more time between the bumps, and then connecting the cart has more time or more distance to accelerate. So as long as you said more time or more distance to accelerate between the bumps, then you're good. Or you could talk about this. So the potential energy differences increase due to increased height between the bumps. So yeah, you could talk about if there's bumps or greater space, then they're going to have a greater height drop between the bumps. So they're going to gain more potential energy between, or they have a bigger change in potential energy, which means they gain more kinetic energy. So you could also use energy there. This is one of those few times where I would say it's a little bit easier to think about this in terms of kinematics. And you won't hear that from me often. All right, C. Now the bumps are returned to the original spacing. The track is tilted to a greater ramp angle theta. So that angle theta goes up. Is the maximum speed of the cart greater than, less than, or the same as when the ramp angle was smaller? Again, I think this is another very solvable question. Yeah, greater. I think this is kind of obvious. Why is this greater? Bigger net force. Yeah, so we can get to the net force when we're not hitting a bump is going to be the weight times sine of the angle. Sine slides down the ramp, right? Or the acceleration is going to be g sine theta, 9.8 times whatever the sine of the angle is. We know as the angle goes up, we know sine theta goes up, at least between 0 and 90 degrees. So we have a bigger angle, bigger sine theta. That means our acceleration goes up. So we have a bigger acceleration. So if we have a bigger acceleration over the same distance, that means we're going to go faster. And this would be relating to that third kinematic equation. That final speed squared is going to be the initial speed squared plus 2 acceleration times the displacement, x final minus x initial. So yeah, so same distance between the bumps, but we have a bigger acceleration, so we have a bigger final speed. And then you can also look at this in terms of energy again. So we could go from looking at each one of these things is like a little mini ramp, right? So I could look at the ramp from here to here, or a larger angle from here to here. So a larger angle, you're going to drop a greater height, bigger change in potential energy, so more kinetic energy gained. So C, you could get 2 more points. Same thing again. Correct answer doesn't earn you any points. And if you select the wrong answer, you get no points. So if you selected the wrong answer, you just get 0. I can't imagine a reason to select the wrong answer for this one. I think they realized, like, hey, we're making this way too hard, and so they gave some points here. But yeah, so acceleration is greater, greater angle, greater acceleration. So you need to say a little bit more than force. Oh, I guess I do expect you to say component of the gravitational force increases. I kind of disagree with forcing you to say that, but yeah, I guess you could say that. So greater angle, you have a greater gravitational force, so you have a greater acceleration. Or again, talking about potential energy. So whenever we tilt this up, we have greater changes in heights between the bumps. So we have more potential energy loss, which means we gain more kinetic energy. More potential energy is converted to kinetic energy between each bump. But yeah, I guess they do expect you to relate it to net force. I guess I'm so. See, these are the things I miss. I guess I'm like, get here and I'm like, so obvious acceleration is g sine theta. I forgot to even think about net force. Those are the reason I miss points. Which is also why you should put everything you know. Questions on those? I think those are not so bad. So then D. I like D. This one is the one that really has some misconceptions or some like really subtle points. Because I guess they weren't like, this is hard enough. They like decided to really mess you up on this one. All right. D. Before deriving an equation for a quantity such as V average, it can be useful to come up with an equation that is intuitively expected to be true. That way, the derivation can be checked later to see if it makes sense physically. So physically, they're just saying, do I have the right values in the right spot? Should I multiply by this? Should I divide by this? Is pretty much all they're getting at. A student comes up with the following equation for the cart's maximum average speed. Average speed is some constant times mass times acceleration due to gravity times sine of the angle of the ramp divided by the distance between the bumps, where c is a positive constant. To test the equation, the student rolls a cart down the long track with speed bumps many times in front of a motion detector. The student varies the mass m of the cart with each trial but keeps everything else the same. The graph shown below is a student's plot of the data for average speed as a function of mass. And now, normally, does mass have an effect of how fast a cart rolls down the ramp? No. So if the cart's just rolling down the ramp, the mass is not going to have any effect on the rate the cart rolls down the ramp. But the reason it will have an effect here, this is like way over the scope of the problem, but it's because it's collision. Every time the cart hits a bump, there's a collision happening. So because there are collisions happening, momentum is important. So mass actually will have an effect here. So yeah, this is this is a crazy question. Are these data, again, data is actually plural, so that is correct wording. Are these data consistent with the student's equation? Yes or no? Average speed is some positive constant times mass times acceleration due to gravity times sine of the angle divided by distance. And then we have some graph here where we have average speed, mass. I'm not going to bother filling out values. So first of all, what is the graph saying? How would I state what the graph is saying in words? So here, notice they're saying, does this make physical sense? We're caring more about as something changes, the other changes in this way. So I'm going to say as mass increases, so according to the graph, As mass increases, average speed does what? Average speed goes up. As mass goes up, average speed goes up, right? And then according to the equation, we see mass in the numerator, which means, so mass is in the numerator, therefore as mass goes up, average speed goes up. So I would say the graph and equation match. Graph and equation agree. That might be kind of getting at the linear thing, though. Oh, they were getting at that one, yeah. Yeah. I thought that was getting at part B. Yeah, so yeah, that's one they were getting at. So when we graph this, let's connect the dots. If I connect the dots, I get a line like this, right? How would I get an equation of a line? What's my equation for a line? Y equals mx plus b. What's my plus b in this equation? Plus 0. This equation is implying my y-intercept is equal to 0. Is my y-intercept equal to 0 on my graph? Y-intercept does not equal 0. So this is kind of the difference. Remember, if this is a linear graph, this is what's called direct linear. This goes through the origin. So a y-intercept of 0. So yeah, so that's what they're getting at here, why this is saying this is no. So yeah, let's kind of look at this. So yeah, so for indicating that the average speed is not, and then I don't like the word not proportional. They're getting at not directly proportional. So let's, looking at this, so they're getting at the point that the y-intercept of the graph is not 0, but the equation indicates that it should be 0. So according to the equation, I have no plus b, so that means my y-intercept should be 0 according to the equation. But according to the picture, I do have a y-intercept. According to the graph, I have a y-intercept, so that does not make sense. Yeah, or you can talk about the slope of the graph is off, so that implies, yeah, I guess they are getting at the relationship. So as you double the mass, then you should double the average speed. But yeah, you could look at, if you did select yes, you can earn a point for saying average speed increases with mass. Yeah, sorry I said that wrong initially. I thought they were getting at that in the second part of this, but yeah. So you see how if I plot this, so those are the two things it's talking about. When I plot this, the line won't go through 0. This equation doesn't have a plus b, so it's implying that this goes to the origin. This graph does not go to the origin. So that's the first thing that's wrong. The other thing that they're getting at is that, say from, let's try to find 2 points for mass. Yeah, there we go. So going from mass 1 to mass 2, according to this equation, if I double mass, I should double average speed, right? If I double mass, I double average speed. So it's a little bit more than just increasing. So yeah, if I double mass from 1 to 2 kilograms, here I should see a doubling in speed. So I should go from 1.5 to 3, but I'm only going from 1.5 to 2. So when I double mass, I'm not doubling my average speed. So that's also incorrect about this. Questions on that? So you do get a point for showing if you selected yes and you showed, hey, as mass goes up, average speed goes up. You do get a point for that. But this graph does not match that. Which, I don't know. I disagree with one of those points, but whatever, because C is a constant, but because that can change your slope. So I disagree with their second point, but that's just me. Can I say average speed and mass result in a rate of change? That's not really saying anything, though. So if you said yes, and you talked about as mass increases, average speed increases, I would say that gets the point. Or if you said something about, yeah, I really dislike how they say that if you double the mass, the average speed has to double, because that's kind of what the whole C does. That C changes the rate of change. So I actually completely disagree with that second point. But the thing that is true is that graph, the equation is implying no y-intercept. Well, the graph has a y-intercept. So that's the correct thing. So if you selected that the data is consistent, you can still get a point if you talk about the relationship that mass goes up, average speed goes up. Yeah, I actually remember now. I didn't think about, well, the first time I did this, I didn't think about that part enough. And then I did miss the y-intercept thing. So really, really subtle, stupid point. 2, another student suggests that whether or not the data above are consistent with the equation could be incorrect for other reasons. So does the equation make physical sense? So now we're pretty much saying we don't care whether the equation matches the graph. Now we're just looking at our equation. This is just asking, does this equation make sense, or is there something else wrong with this equation? Not looking at the graph. I'm going to say no, the equation still doesn't make physical sense. What's the thing that doesn't make sense? Distance. Yeah, what doesn't make sense about distance? So the equation is saying larger distance between the bumps yeah, that's saying that the equation is saying larger distance. If I make my denominator bigger, that means this gets smaller. So the equation is saying if I have a larger distance between the bumps, I'm going to have a smaller average speed. Reality, not realty. I think there's two else. I don't know. I really tired today. Reality, we have a larger distance between the bumps. gives a larger average speed. So yeah, these don't match. And let's look at this for the point. So no, again, not earning points for that, but the only thing we're earning points for are our explanation. So average speed, wait, no, that's one. So yeah. So oh no, I take that back. They actually did give you a point for selecting no. So the distance depend. Oh no, never mind. You have to say distance dependency is incorrect. So yeah, so if you say that the distance is the thing that's wrong, you got 1 point. So if you just said anything about distance, you got a point. And then comparing this to relationship, so pretty much saying the contradiction between the inverse relationship and part B. So pretty much saying what I said, how the equation shows that a larger distance would result in a smaller average speed, but we expect a larger distance between the bumps to have a larger average speed. So I've given this one as a question on a mock test before, and the average was pretty bad. Did anyone get over half the points? Because over half the points would be extremely impressive on this one. Got four. Four beat the average. I forget. The average on this one was either like 1.8 or 2.5. So yeah, nine is extremely impressive. 4 is still good. It's not the best, especially with everything free response. That's 33. Hopefully they don't put a question like this. I genuinely dislike a lot of things about this question, but if it makes you feel better, this was the second year that they were doing the AP test, and so they were still struggling with difficulty, and they really have been easing up on the difficulty a little bit more recently. So yeah, hopefully they don't give a cursed problem like this one. I jinx it. Yeah, I don't believe in jinxes. Any questions about this before I go? I can answer for everyone else. Well, I think I'm going to stop recording now. So for everyone here, you can stick around and still ask questions after I'm finished recording. But for people listening to the recording now, again, go through, look at the sample that I posted. It's on the stream on Google Classroom. Look at that sample. That's a really good sample of how to go through and do this. Focus a little bit more on the end of the first question because you won't have a procedure question. You won't have an experimental design question on this year's AP test, but I could still see some aspects of that being asked. Go through the second one is difficult, but make sure go through, do it, grade yourself based on the rubric, clearly mark your points, and then go through anything you did not get full points on. Go through and on either a separate part of the paper or on a separate page, clearly do your corrections on there. Again, I won't see you until next Monday. You do have Friday off, so nothing will be posted on Friday. I'm not going to make you do anything on Friday. Teachers shouldn't be making you do anything on Friday, so hopefully they're not. They can assign you work over the weekend, but they can't make you do things on Friday. So yeah, so do this one. We're going to keep doing AP test review like this for a while longer. Yeah, make sure you keep getting in late work. The grading cycle does end this week, but I don't know what's happening with that. Apparently there was a meeting yesterday with the school board and everything, but I still haven't heard anything back from that. So yeah, I'll kind of relay that to you when I hear it. So other than that, everyone have a good 3-day weekend and just make sure you're keeping up and getting your work in. I always click on one. There we go.